So many of you have asked that same question over and over again. I know some of you can't even sleep at night because you're wondering what might be the answer to that question. And the question, of course, is why are databases so cool? Well, I think there are three reasons for that. The first is databases have to do with normal forms. You all learn about that in your undergrad course. That's the first, second, third, boys called normal form and so forth. And that's really, really cool. You think it's boring? Well, yeah, it's a little boring here and there. It's important, but it's boring. Okay, but there's a second reason why databases are so cool, and that is entity relationship modeling. You all learned about that. It's also boring. Yeah, okay, but there's a third reason why databases is cool, and that's SQL, the structured declarative query language. It's really, really beautiful, easy to read. You immediately grasp what the query is about, and you also don't like that too much, you're saying? Yeah, okay, yeah, I understand the problem. It's true, normal forms, entity relationship modeling, SQL, maybe it's not too exciting, although it's super important in order to build a database system, to use it as an application developer. However, all of this is about using a database management system, which is not so exciting for computer scientists sometimes. The interesting thing is really looking under the hood, so not using a database system, but understanding the technology that's under the hood in the database system. So we need to rephrase the question to why is database technology so cool? Well, and that has many, many reasons. Important to understand is database systems is actually a vertical topic. So what that means is database systems covers at least 6 different things, 6 different sub-areas from computer science. Let's go through them. So the first is data layouts. What is a data layout? Well, if you have a table, say with 3 rows and 3 columns only, eventually you need to map the data in the table to your storage media. Let's assume you want to map it to DRAM in main memory. Then you have the problem that the table is a 2-dimensional address space, whereas DRAM is a 1-dimensional address space. So you somehow have to find a mapping from the left to the right side. This may sound trivial, but it's very important and it may make a huge difference in performance. We're not talking about a few percent, we're talking about orders of magnitude, factor 100, factor 1000 in query performance. So you could do that row-wise. You could say, okay, I first store 23, then Albert, then 45,000, then 42 Rob, and so forth. This is called a row-wise layout or a row store. But you could also do that in a different way. You could do it in column order. So 23, 42, 77, Albert, Rob, Peter, and so forth. This is called a column-wise layout, and this is used in column stores. Again, it may look trivial, but it may make a huge difference in terms of overall performance of your system. So you better know about that. In this course, we will look at the different data layouts that are useful when designing database systems. The second thing that's very important in database systems are data structures. A data structure is typically something like a tree. Unfortunately, outside in nature, the trees are like upside down, so we have to turn them around like that. They look more similar to a binary search tree. In a binary search tree, you eventually traverse the structure from top to bottom. And maybe you learned already that some binary search trees are optimal. There are balanced versions of binary search trees like ABL trees that are optimal. However, what does optimality really mean? Because there's also something like the storage hierarchy. Maybe you heard about that already. So a computer system usually has very different storage media, and this is organized in a storage hierarchy. So what that means is there's a CPU that's sitting in the middle or on top, as you wish, and the CPU is connected to different storage levels. So the L1 cache, L2 cache, L3 cache, main memory, flash, and hard disk, and so forth. And the further you go away from the CPU, the higher the capacity of the storage level, and the higher the access time, the slower the media. This is depicted with the arrow on the left. The closer you get to the CPU, the higher are the costs for the different media. So L1 storage is more expensive than L2 and so forth. In addition, the bandwidth also increases. The amount of data you can stream from a storage level to the CPU is higher the closer you get to the CPU. So you can stream more data from L1 to the CPU than from L3. This storage hierarchy is very important and has to be factored in when designing index structures. Because what may happen in a binary search tree is something like that. If you traverse a tree, it may actually happen that the data you're looking at is not available on one of the caches. So you have to go to main memory. And that makes a huge difference whether the data item you're looking at is in L1 or L2 or is in main memory. So if it's not in the caches, you have something that's called a cache miss. And those cache misses may add up pretty quickly and have a huge impact on the overall access time of the tree, even if you use a balanced tree. So this tree is not so well balanced, but even if it's balanced, this is a problem. One thing you will learn in this course is that balanced binary search trees are optimal in a theoretical sense, but they are not the fastest thing you can do in a database system. Because to really design index structures that are efficient, in reality, you need to factor in the storage hierarchy. And we're not talking about a 10 or 20% difference. We are talking about a factor difference in performance. The third thing that's very important in database systems are algorithms. Algorithms are very close to cooking recipes. Assume you want to make a bread. So you get a function, make bread, you have a list of ingredients as parameters, and then you can go through that stepwise. So you initialize the bread, you initialize the oven, then you add flour to the bread, you add salt to the bread, you add water to the bread. And then there's a little while loop that checks whether the bread is smooth. If not, you keep on kneading the bread. Then you wait for 40 minutes, then you set the heat in the oven, then you wait another 20 minutes, the oven has to reach that heat, then you roll the bread into a round shape, then you put it into the oven, and so forth. So algorithms are very close to cooking actually, and they play a tremendous role in database systems. For example, in databases you have this declarative query language, SQL. It defines what you want to have. So if you want to have all data from a table, say Fotografen, which means photographers, with a certain condition, eventually the database system has to translate that into a program that actually gets the data out of the database system. So the cool thing about database systems is you don't have to worry about the right side, the program, if you're just a user. But if you really want to understand the technology, you better understand how this translation process is happening. So this is very close to a compiler, what a compiler does. The compiler translates a programming language into efficient binary code. And that is what a database query optimizer does in some sense as well. So it gets as its input the left side, the declarative SQL statement, and has to translate that into an efficient program. And there are many important things to learn about that. So the fourth thing that's very important in database systems is hardware. So hardware keeps on changing. In the past, database systems were designed for hard disks. But nowadays, many database systems fit entirely into main memory. Main memory is getting cheaper and cheaper, and therefore, for many scenarios, you can put all of your data into main memory. However, that again affects how the database system is designed internally, because the data structures, the indexes, the algorithms you're using for disk are different from the ones you should be using in main memory or any other future storage media. Depending on the hardware to use, what is the right set of algorithms and data structures in the database system? The fifth is, so very often in computer science we focus on the little things. So assume that there's a little piece in your system like this screw, and then you can optimize the screw in a zillion different ways. But you always have to factor in that this little piece, this screw, is part of a bigger system. So this may be just one little tiny piece, say in a jet engine. And then it's not enough to concentrate on the properties of the screw. You better also understand the context, the system that is using this screw, because that may impact the design of the screw, the design of that single piece. And then again, that jet engine may be part of an even larger system like this Airbus A380. So it's usually very risky to just over-focus on the single pieces. You have to keep in mind the entire context where that piece is used. And one thing you will learn in this course is that a complex software system is way more than the sum of its pieces. So it would be very risky to only assemble the individual pieces, ignoring the properties of the overall system. The final thing that's important in database systems are the users, of course. Those may be the end users that access a database, but the users may also be application developers that just use a database system as one building block in their software stack. Users somehow have to interface with the database system. Well, and the interface may be pretty ugly, or it may also be pretty nice. And maybe you want to worry a little bit about that. How is the user interfacing with the database system? Because if it's an ugly, unusable interface, then the user might not be willing to use the system. So we will also look a little bit at that. So, in summary, database systems is a vertical topic covering aspects from 6 different areas. And we will touch all of those areas in this course. Now you might wonder, well, why should I care? I think, why should you care about this course? Why should you care about the internals of a database system? Right. I think you can pick any out of 4 reasons. So the first is, this stuff is simply interesting. So you will see that the technologies that are used inside a system is interesting, and it's fun to juggle with those ideas and algorithms and data structures, play around with that. You can learn a lot, not only stuff that's relevant for data management, but stuff that's relevant for computer science in general. The second reason is, it has a huge impact on your software. So your software, at the end of the day, will manage data. So be it that you initialize a simple variable, that you have data in an array, or you create a hash table, or you actually connect to a database. Software is about handling data. And how to handle that data has a huge impact on the overall runtime of your software. Even if you don't use a database system, the techniques are the same, and you better understand how to effectively manage data, be it by using a database or be it by initializing certain index structures, like a hash table. It's just a special case of an index structure yourself. So you better understand how to manage data in your software. And that is also one part of this course. So it has a huge impact on your system. Again, we're not talking about the 10% improvement. If you manage data in the right way, we might be talking about 3 orders of magnitude performance improvement in your software. The third reason why knowing about the technology under the hood in a database system is important is it gives you a competitive advantage. I mean, many people can use a database system. They can create a few tables and write some SQL statements, and that's all cool. But if it then comes to performance issues, consistency in making it really work, you will see that understanding what's under the hood makes a difference of a true expert versus someone who's just configuring the database, who is using the database without really understanding what's going on inside in terms of algorithms, indexes, and data structures. And the fourth reason why all of this might be interesting, there are currently exciting opportunities in data management. So be it in research, in industry, and even in startups. So actually there's a lot of venture capital being given to startups in the area of data management. And that's kind of interesting because maybe some of you think that, well, database systems is a mature field, right? I mean, they have been doing that for the last 50 years or so. And I mean, all these products are super cool. But one thing you will also learn in this course that that's not actually true. There are many, many opportunities and many surprising new discoveries that have been made only in the past few years. And they really changed how people manage data these days. So you will learn in this course, there's a lot of exciting development going on in database systems, really changing fundamental aspects of how data is managed. You'll find more database stuff at one of my web pages, so datenbankenlernen.de has a list of all the videos. There are videos in English and in German. You can also look at my YouTube channel, or you check out our webpage, infosys.uni-saarland.de.